In this video, we're going to take a look at parametric equations. So the idea is to create a pair of equations, one that gives us x and one that gives us y. So in other words, we're going to introduce a new variable. Every point on the graph is going to have coordinates x and y. And we're going to use this new variable to find x and find y. Usually that new variable is the variable t in parametric equations. And so we're going to find x and y independently using this new variable of t. If we do that, basically what we're going to have is a function that gives us the x value and a different function that gives us a y value. So for any value of t we plug in, we get a corresponding ordered pair. That's the idea of parametric equations. Parametric equations are a pair of equations, one that gives us the x value, one that gives us our y value, with parameter of t. Often we think of t as being time. All right. So one way to think of this is think about tracking movement through a plane. So we move through a plane at any one given time. We are at a specific place in the plane. So that's the kind of overall concept. We're tracking the movement, and it's the movement through, in this case, a plane over a specific period of time. Now, obviously, we can graph a curve in the plane through parametric equations because we can plug in any numbers in the domain and get a corresponding ordered pair x and y. And then we can put those all together and they become a curve in the plane. The parametric equations together with the graph are called the plane curve. So again, the extra variable helps us out because creating an equation gives us the ability to tell when the graph is at a point. Also, it's going to allow us to graph things that don't have nice equations in rectangular coordinate systems. So I, things where it's hard to graph y is equal to a function of x. And because of that, sometimes parametric equations can be easier to do calculus operations on than other equations, our standard rectangular coordinate system equations. So in this section, we're going to sketch some graphs of parametric equations. We're going to change back and forth between rectangular and parametric equations. Rectangular is what I'm saying is just the x, y. Y is equal to a function of x, or we have x's and y's in our equation. And we're going to change those back and forth to parametric. So let's start by graphing some parametric equations, and I'll use plotting points to do the graphing in this example. My set of parametric equations is that x is equal to 1/2 t squared, and my y coordinate is going to be given by 3 times t to the 1/2. There's a lot of different notations people use in parametric equations. Some people use x of t, like the x value is a function of t, and this is that function of t. Other times you'll see x is equal to f of t, or sometimes you'll just see x is equal to. But it all means the same thing. The x value is given by this equation. The y value is given by this equation. So all we would do is start plugging in different values for t. And let's say we want to plug in a t value of 0. When I did that, I plug in 0 into the x equation. 1/2 times 0 squared would give me 0. Into the y equation, 3 times t to the 1/2 would give you 3 times 0 to the 1/2 power, which would also be 0. So at time 0, we're at the origin, right? We're at the point 0, 0. And then you can start plugging in any other number. So if you plug in a t of 1, for instance, the x value is going to be 1/2 times 1 squared based on this equation. So we're going to get 1/2 for the x value. The y value is going to be 3 times 1 to the 1/2 power, which is just 3. So at t of 1, I'm at the point 1/2, 3. And then you can plug in other values. Notice that, by the way, it won't let you plug in negative values for t because of the 1/2. So the domain of t is from 0 to infinity, positive infinity. So that's why I'm not plugging in negative values there. But plugging in 2, I get 1/2 times 2 squared, which is a 2. And then when I plug in 2 into my y, I get 3 times the square root of 2. So 3 times root 2 is the y value. I'll plug in a 3. 1/2 times 3 squared. So that's 1/2 times 9. That's what gets you your x value. That's 4.5. When I plug in 3, I get 3 times 3 to the 1/2 power, which is 3 root 3. So I'll write that out as 3 root 3. When I plug in 4, 1/2 times 4 squared is 8. So we're putting in an 8 there. And then when I plug in 4 here, 3 times 4 to the 1/2 power. 4 to the 1/2 power is 2, so 3 times 2 gives me a 6. And we can basically do anything. It's kind of nice. I'll plug in one more. Let's say I plug in 9. 1/2 times 9 squared is going to be 40.5 as the x value. When I plug in 9 here, 3 times 9 to the 1/2 power, that's 3 times 3, I get 9, it turns out. And what I could do is I could plot these points on a graph and then kind of connect those dots. So I've done that. I've graphed some of those points that we just found. Again, I'm just graphing the x, y coordinates. There's no t coordinates to graph. The t is giving me the point. So at time 0, I'm at this point, 0, 0. At time 1, I'm at the point 0.5 comma 3 or 1/2 comma 3. At times 2, I'm at 2 times 2 comma 3 root 2. That's about that number. And then I plugged in 3. I got 4.5 comma 3 root 3. That's that decimal. And then I plugged in 4. I got an 8.6. And if I scroll out, 40.5 comma 9 was what I got when I plugged in 9. You can kind of see what's happening here. I'm going to be getting a graph that goes through these points and then shoots out. I didn't draw that very well, but you can see that's the kind of graph that we're going to get. Now, there is an actual way to graph using Desmos, and there is an actual way to graph using your calculator. I'll show you how to graph parametrics on your calculator in another video, but on Desmos, what you do is you create an ordered pair. One that says the first coordinate, which is your function that gives you your x, so 1/2 t squared, and your second coordinate is the one function that gives you your y. So you graph it like this, 1/2 t squared, comma, 3t to the 1/2 power. And then you let t range from certain numbers. Right now, t in my graph goes from 0 to 10, and so you can see how far out it goes. If I went to 100 with my t value, then you'd see it goes even further. You can try to plug in some negative numbers. Obviously, if you plug in a negative number, since that doesn't work for my y term, we're not going to get anything with the negative numbers. But there it is. There's the graph that we're looking for. This means if I want to graph by hand, I can obviously plot some points and then connect the dots. But now we know a way to graph in Desmos. And like I say, I will put up another video which shows how to graph parametrics with a TI-84. If we are trying to do a graph, if we're trying to create a graph using a set of parametric equations, if you want to, you can plot points if you want to plot points by hand. We will show how to use technology a little bit later and maybe in another video with the TI-84. We saw that really quickly with the this past Desmos example. But another way to graph is converting into the rectangular equation and then using the graph of the rectangular equation that we may be able to recognize. There are these three options. There may be more, but these are the three options. So let's talk about that middle option for a while, the converting to rectangular, or going back and forth between parametric and rectangular equations. Let's start with a parametric equation and convert it into a rectangular one. We're going to have two basic tools to do that. One is what I refer to as a direct substitution. That's basically if I solve one of the equations for t and then substitute in to my other equation. Then there's the tool of indirect substitution using some identity that we already know. We'll show that a little bit later. Let's start with the direct substitution. Let's say we want to convert this pair of parametric equations into a rectangular equation and then graph it. The parametric equations are x is equal to t squared minus 4 and y is equal to t over 2. In this example, in the first equation, it's hard to solve for t because when I solve for t, I'd have to take a square root and then I'd have positive and negative square roots. However, in the second equation, it's really easy to solve for t. So the second equation has y equals t over 2. If I simply multiply both sides by 2, I end up with 2y is equal to t. Now we're going to plug that in to the other equation, meaning I'm going to replace t in the other equation with a 2y. So I start with x equals t squared minus 4. And then I simply replace this t, now that I've solved for t, with a 2y. Make sure that when you do that, you put that in parentheses because technically the 2 and the y both get squared. And there you go. X is equal to 4y squared minus 4. We know that that equation is going to give us a parabola, specifically a parabola pointing to the right. And it's pretty easy to graph this parabola if we want. So here is the graph of that parabola, okay? By the way, again, just to point out, you can actually graph that same parabola in parametrics on Desmos if you want using the x comma y, where x becomes your x value, your x function finder, and y is the expression to find y. So that's another way to do it. If you do graph on Desmos, you have to be careful graphing parametric equations because if you use the wrong t, then you only might get half the graph. So you have to make sure you have the correct range, or excuse me, not the correct domain for the t. All right. But that's it. So notice that we're getting the same graph. And so that's one way to do graphing is just convert to rectangular and then graph the rectangular equation like we normally would, plugging in points, plugging in values, finding points, connecting dots, et cetera, et cetera. Let's look at a couple of other examples. In example 3, I'll just convert the parametric equations into a rectangular equation, and I'll just graph the rectangular equation in Desmos. So here we have x of t is equal to 5 minus 8t, and y of t is equal to 4t squared plus 3t. You can try this on your own if you want by pushing pause, and I'll do this in a couple of seconds. So let's do this. We want to convert these parametric equations into a single rectangular equation. And we know that the rectangular equation and the parametric equations will have the same graph. In this situation, it's going to be easier to solve for t in the first equation, so that's what I'm going to do. Usually I adopt the notation where we just write x is equal to a function of t, or an expression in t when I'm solving. Even though I have x of t as the notation, I'll write x equals 5 minus 8t and then solve for t. So we're going to subtract 5 from both sides. And then divide by -8, or multiply times -1/8. We get -1/8 times x plus 5/8 is equal to t. And then we can plug in that expression in for t into the second equation. So I take this y of t equation. I will just again use the notation y equals. It'll make my life a little bit easier. And then everywhere I see a t, I replace it with -1/8 x plus 5/8. I can simplify this if I want. I can multiply this out and do the simplification. And you can do a lot of rewriting and all of that as well. But that is the actual answer. I don't think I'm going to simplify in this case. But like I said, if you want to, you can. You can rewrite this. You can do all kinds of stuff. Let's go ahead and just graph this as it looks right here, or if maybe it's a little bit easier to see this way. The -1/8 times x plus 5/8, I can think of that as -x plus 5/8 as a single fraction. And so I might write it something like that if I choose to. That might be easier to write and type in to graph. Might also be easier to compute with as well. So in the rectangular coordinate system, I get this parabola. Again, you can just plot some points if you want to do this by hand, or you can use some tool like I'm using here. So that's how we can convert um, in this case. Now, let's do another example. And let's convert this set of parametric equations into a singular rectangular equation and then graph it. Now, in this instance, we'll have to watch the domain, and we'll go over that when we get to it. Once again, just like the last problem, it'll actually be a little bit easier to solve for t in the first equation. So that's what I'm going to do. We have in the first equation, x is equal to the square root of t plus 1. And so what I'm going to do is subtract 1 from both sides. And then because we have a square root there, we have to square both sides. I get x minus 1 quantity squared is equal to t. Then I plug in that t into the second equation. The second equation is just y equals 5 times e to the tth power. I replace the t with x minus 1 squared. That'll give me y is equal to 5 times e to the x minus 1 quantity squared power. So that's what we get. That is the rectangular equation that represents this pair of parametric equations. Now, I want to say something. If I graph just this equation and I let x be anything that I want it to be, I'm actually going to get not the equation, not the same graph as I would here. Because in my original parametric equations, t had to be 0 or higher in order to graph it. Because of this square root of t, I needed to plug in t values that were greater than or equal to 0. That translates to x values that are greater than or equal to 1, since x is the square root of t plus 1. So basically, the domain here, if I want to have the same graph, x needs to be greater than or equal to 1. So it is this equation on this domain that actually works. That gives me the same graph as my set of parametric equations. Again, x needed to be greater than 1 since t had to be 0 or higher. Let's graph these and see how this works. I've, again, just graphed this on Desmos. I'll show you in another video how to graph this on your calculator. But y equals 5e to the power x minus 1 squared gives this graph here. Graph pointing up, very steep, obviously. Lowest value there is 1, 5. Now, this is for all x. You can plug in any x you want. You can plug in positive and negative x's. I actually don't want that. My parametric equations are just going to give me the right-hand side of that graph, the one where x goes from 1 and higher. Because I can't plug in square root of a negative number and get something that I can graph on my xy plane. So y equals 5e to the x minus 1 squared power is not the same, but it is the same if I choose to restrict my domain from 1 to higher. So essentially, for x greater than or equal to 1, I do, in fact, get the same graph. So that's how we can convert parametrics into rectangular equations using direct substitution. Okay. Now let's go the other way. Let's convert rectangular to parametrics using essentially the same technique, but in reverse. We're going to use direct substitution, but in reverse. So we're going to take a rectangular equation. We're going to do direct substitution. Hopefully we can solve our rectangular equation for either x or y, and then do a direct substitution for the other variable. So here's a nice quadratic equation that's already solved for y. Let's convert this rectangular equation into a pair of parametric equations. I think in this case, I won't graph. I'll just leave off the graphing. We know how to graph this quadratic, this parabola. So in this case, we have that our equation is already solved for, in this case, y. Okay, we already have y equals. So what I do is I set x equals any expression that I want. So if I wanted to, I could set x is equal to 3t plus 4. Or I could set x is equal to 3t squared plus 4, or 3 times the square root of t plus 4. You get the point. We can set x equals anything that we want, where that anything we want is some function in t. Now, the easiest thing to do is set x equals to t itself. If we do that, then my y equals 5x squared minus 4x plus 2 can be rewritten as 5 times t squared minus 4 times t plus 2. And that gives us our parametric equations. So our set of parametric equations is just that. X equals t and y equals 5t squared minus 4t plus 2. Now, obviously, if you chose x equals some other expression, some more complicated expression, then that would be fine as well. We just have to use the more complicated expression So if I set, for instance, x equals 2 times t squared minus 7, then what I could do is replace every x with a 2 times t squared minus 7. Or any other thing. So no matter what you choose as your expression for x, you just plug that in for the x, and then you get a function for y. So if I can have y equals a function of x, then we can make this into a set of parametric equations by direct substitution. Let x be anything you want, and then plug that in for the function expression for y. Typically what we do in the standard cases, a lot of times I let x be equal to t. That way, I don't have to be really particular about the domain. Here, notice that the smallest value for x you can get is a -7. And that may throw my problem off. In fact, it does. This set of parametric equations is the same, gives me the same graph as this, but only for x values greater than or equal to -7. This set of parametric equations gives me the exact same graph, and I can have x go all the way to -infinity. So this set gives me the exact same graph, but doesn't have the same domain. So again, that's one of the reasons I tend to let x be equal to t when I do the substitution. Hopefully that all makes sense. Let's do another example. On this one, it says we want to convert the rectangular equation into a pair of parametric equations. In this example, we have y squared minus 5 times y to the third plus x equals 7. It's pretty obvious that in this example, it's going to be much easier to solve for x than it is going to be to solve for y. So that's what I'm going to do. I'm going to force the x on one side of the equation, and we'll get x equals an expression with respect to y. And that way I can do my direct substitution. Let's go ahead and do that. Subtract y squared and add 5y to the third to both sides. So if I add 5y to the third, I'll get 5y to the third on the right. If I subtract y squared, I get minus y squared on the right. And then I also have this plus 7 that's still on the right-hand side as well. So rewriting that equation, just solving for x, I get x equals 5y to the third minus y squared plus 7. So instead of setting my x value, I'll set my y value to be t, and then simply replace the y value with t in the x equals expression. I end up with 5 times t to the third minus t squared plus 7 as my x. So x equals 5t to the third minus t squared plus 7, and y equals t as my pair of parametric equations. And that's it. That's the whole thing. Obviously, you could have used anything you wanted for y, any expression. Y is equal to any expression with t, although you do have to be careful about the domain in some cases. In some cases, we get all domains. So for instance, if I said y is equal to t to the third, actually, let me just do another one. Sorry. So if I let y equal t to the third, then replace every y I see with a t to the third when I have that. And I could have just as easily done that. And my domain would be still all real numbers for my y value. My y could attain all real numbers. If you did that, t to the third power is t to the ninth. T to the third to the second power is t to the sixth. So these are two options that again give you the entire real numbers as your domain of t, which is your entire real numbers as your domain of y. And I believe you get the entire real numbers as x as well. But there you go. Again, most of the time when I do this, I keep it as simple as possible. I let one variable equal the t value. In this case, it was easier to let y equals t. In the previous case, it was easier to let x equals t. X equal t. All right, let's do one more example with this equation. Square root of y plus the square root of x is equal to 5 times e to the x power minus 4 times x. We want to convert that rectangular equation into a pair of parametric equations. Actually, I won't graph this one again. I will just leave this one ungraphed. But do the conversion. If you want to do this on your own, then push pause on the video. I will do it in a couple of seconds. All right, in this case, it's going to be probably easier to solve for y, so that's what I'm going to do. I'm going to subtract the square root of x from both sides. And then I'm going to square both sides. If I square the left-hand side, I just get y. If I square the right-hand side, I get 5e to the x minus 4x minus square root of x. All of that being squared. So all three terms on the right are being squared. Obviously, it's easier to set x equals t in this example. So we're going to set x equals t. You could use any value you wanted, any expression you wanted for x, but again, the simplest is just x equals t. And y is going to then be equal to that big quantity being squared. The quantity there is 5e to the t power minus 4t minus the square root of t. All of that being squared. So that's it. And if you wanted to graph it, obviously you could graph it using plotting points or plugging it into some technology. So anytime we have an equation where we can solve for y, or an equation where we can solve for x fairly easily, then we can let the other variable just be t or any other expression that we like, and substitute that variable out and replace it with t or whatever expression we like in our original rectangular equation. So that is the essence of direct substitution. Now let's take a look at what I call indirect substitution. With indirect substitution, we're going to use some identity with our substitution. And in this class, the identities that we use most often are going to be the Pythagorean identities. That is cosine squared plus sine squared equals 1 of whatever angle. So cosine squared of an angle plus sine squared of the same angle equals 1. Or the other Pythagorean identity that we use a lot is 1 plus tangent squared of an angle is equal to secant squared of that angle. Now, I want to state that this isn't the only way to do indirect substitution. We had a lot of trig identities, and technically you can use any of those. But these two are the ones that are going to be most applicable in this class. So let's say we have a pair of parametric equations, and we want to turn this pair of parametric equations, one of which involves cosine of t and the other of which involves sine of t. We want to turn those into a single rectangular equation and graph it. Because one of these involves cosine and the other involves sine, one of them is cosine of t, one of them involves sine of t, what I can do is I can take my equation that is essentially x equals 6 times the cosine of t plus 5, and instead of solving it for t, what I'll solve it for is cosine. So I will subtract 5 from both sides, and then divide by 6. This tells me that x minus 5 over 6 is equal to cosine. There it is. So, oh, so that is cosine of t. Now, in my other equation, I'll solve for sine of t. We have y equals 6 sine of t minus 2. Add 2 to both sides, and then divide by 6. That would give y plus 2 over 6 as sine of t. Here is where the indirect substitution comes in. I have one equation solved for cosine of t. I have another equation where I've solved for sine of t. But we know that there is this identity, the Pythagorean identity, which says cosine of any angle squared plus sine squared of that same angle has to add to give us 1. Now we do a substitution for cosine. We substitute in x minus 5 over 6 for cosine. And we substitute y plus 2 over 6 for sine. When I do that, I will get x minus 5 over 6 quantity squared plus y plus 2 over 6 quantity squared is equal to 1. This gives me a rectangular equation through the use of this Pythagorean identity. Now, I can rewrite this equation if I'd like. In fact, I'm going to do that in this case. If I square both the top and bottom, I'll get x minus 5 squared divided by 36. And then I'll get y plus 2 squared divided by 36 is equal to 1. So both denominators will be 36. And I'll multiply both sides by 36. That will give me an x minus 5 quantity squared plus quantity y plus 2 and quantity squared equaling 36. Notice what this is. This set of parametric equations is the same as this rectangular equation. This rectangular equation we hopefully can recognize is a circle of radius 6. And the center of that circle would be at the point 5, negative 2. So it's the circle of radius 6 centered at the point 5, negative 2. So it's that conic section. Let's go ahead and graph both the rectangular and the parametric equations there. Again, I will do this on Desmos, but you could also do the same thing with your TI-84 calculator. So I've just typed in the equation x minus 5 squared plus y plus 2 squared equals 36. Obviously, I've also graphed the center at the point 5, negative 2. So that's a pretty standard, again, circle, radius 6, centered at the point 5, negative 2. If I wanted to graph this using parametrics, I would just write parentheses 6 cosine t plus 5, comma 6 sine t minus 2, end my parentheses, and then choose values of t that work. Now, if I want to circle, if I want to go around the circle one time, you can actually just go from 0 to 2 pi, and that will take you one loop around the circle. If I go from 0 to just pi, then I get the top half of the circle. Obviously, you can go from something like -10 to +10. That will give you multiple paths around the circle. One thing I like to do is on occasions with parametrics, what we can do is I can copy this parametric point and then instead of putting in a t, just put in an arbitrary value, like a variable value. We'll call it a for this case. And you can move that a around by increasing the value of a, and you can kind of see how the point is moving along the circle. In this case, we can see that each time or each movement, it's moving that point around the circle in a counterclockwise direction. We'll talk more about that a little bit later. But that's one nice thing you can do is you can track a point. And that's really the goal of parametrics is to track where you are at a specific point in time and so the path that this purple point is taking is the blue path. And so we can see that purple point moving around our circle. This example gave me a circle of radius 6. If you want, you can try this one on your own, push pause, and then graph this, convert it into a rectangular equation, see what you get, and then think about what the graph of that is. Again, if you want to try this on your own, push pause. I will do it in a couple of seconds. Here we go. Since this set of parametric equations involves cosine of t and sine of t, I am anticipating that we're going to use the Pythagorean identity that says cosine squared of t plus sine squared of t is equal to 1. And therefore, I'm going to solve the x equation for cosine of t. Solving this equation for cosine of t, I'd have to add 4 to both sides and then divide by 2. That would give me x plus 4 divided by 2 is equal to the cosine of t. Now let's do the equation for y. We have y is equal to -5 times the sine of t plus 1. I would subtract 1 from both sides and then divide by a -5. That would give me y minus 1 over a -5 is equal to sine of t. At this point, I can use my Pythagorean identity. Cosine squared of t plus sine squared of t is equal to 1. So I'm going to replace the cosine of t with x plus 4 over 2. And then I'm going to replace the sine with a y minus 1 over negative 5. Let's go ahead and do that. In this case, the denominators will not be the same when I do the squaring. But what I can do is I can write out this a little bit different into something that we're going to be able to recognize a little bit easier. The only thing I'm going to do is I'm going to keep the numerator as x plus 4 and keep the squared over around the entire x plus 4. And the denominator I'm actually going to square. 2 squared becomes 4. In my other fraction, in my other piece, I'll keep y minus 1 inside of parentheses, the squared on the outside. I will square the denominator. Negative 5 squared is 25. Notice what I get here. This is the standard form for the equation of an ellipse. This ellipse is stretched out more in the y direction than it is in the x direction. We could find all of the features of this ellipse using what we know about conic sections. But that being said, it's just very nice that these two parametric equations, this set of parametric equations, wound up giving me the equation of an ellipse. I'm going to graph this using Desmos. Of course, you could graph this using your calculator as well. Here is that graph. So the graph of the ellipse, as you can see, it's stretched out more in the y direction than it is in the x direction. That is the graph of the ellipse in the rectangular coordinate system. If I do parametric, I get the exact same thing. So whether I'm utilizing the parametric or the rectangular, we're getting the exact same ellipse. Obviously there, the center of that ellipse is negative 4, 1. We could find the other features of this ellipse using all of the conic section stuff we did before. I do want to state something about this ellipse that's slightly different than the circle we did. As the t value increases, the point will move around the ellipse in a clockwise direction this time. So as the value of t increases, as it gets bigger and bigger and bigger, we're moving around the ellipse clockwise. Again, that is just an interesting observation. Let's do another example. This time, instead of having cosine and sine, let's utilize secant and tangent. If you want to try this on your own, using the secant tangent Pythagorean identity, go ahead and do that. Otherwise, I will do that in a couple of seconds. Now, you probably anticipate correct that because we're dealing with secants and tangents, we'll utilize the secant tangent Pythagorean identity. And so we'll solve for secant in the x, and we'll solve for tangent in the y. Let's go ahead and do that first. X is equal to 4 times the secant of t minus 5. When I solve for x, I'll add 5, or excuse me, not solve for x, excuse me, solve for secant of t. I will end up with x plus 5 all divided by 4. So I'll have to add 5 to both sides and then divide both sides by 4. And that will be the secant of t. In my equation with the y is equal to 6 times the tangent of t minus 2. So if I add 2 to both sides and then divide by 6, we'll get y plus 2 divided by 6 is equal to tangent of t. At this point, we employ the Pythagorean identity with secant and tangent, which says 1 plus tangent squared of any angle is equal to secant squared of that same angle. In particular, it'll work for t. Now I just replace tangent with y plus 2 over 6, and I'll replace secant with x plus 5 over 4. So I can do that through copy and paste very quickly, I think. One plus tangent squared is equal to secant squared. So 1 plus the quantity y plus 2 over 6, quantity squared, is equal to the quantity x plus 5 over 4, quantity squared. I'm going to rewrite this into something that's a little bit easier to recognize. And in particular, let me start by doing this. I'm going to subtract y plus 2 over 6 squared from both sides. And what that'll give me is something that looks like 1 is equal to x plus 5 over 4 quantity squared minus y plus 2 over 6 quantity squared. Now I can put the 1 either on the left-hand side or the right-hand side. The right-hand side is going to be a little bit more familiar. And now hopefully you can see that this thing is actually just a hyperbola. We got x plus 5 quantity squared divided by 16 minus y plus 2 quantity squared divided by 36 is equal to 1. That is the standard version of a hyperbola. With cosines and sines in our first couple of examples of this indirect substitution, we saw we got circles and ellipses. Now, with secants and tangents, I end up with a hyperbola. Let's go ahead and graph this hyperbola, both in the rectangular form and in the parametric form. You can graph that using Desmos like I will, or you can graph it using your calculator as well. I have done that already. X was 4 secant of t minus 5, y was 6 tangent of t minus 2. We got this hyperbola that I have graphed. Obviously, it is center. It has the center at -5, -2. That's fairly easy to see. And it doesn't matter whether you have the parametric or the rectangular version, you get the same graph. However, the parametric version also, you can utilize how fast you're moving along this graph. And notice what's happening. Basically, what happens is that this point comes into the graph here, let's say, and it's going to trace out all the way to the other end. And then when it gets close to that other end, it's going to jump all the way down into the right. So watch what happens. It starts going up here, and then it'll jump down into the right. And then it'll trace over here. As it moves up to the right, then it'll sort of complete the loop, hopefully on this left-hand side. And it just keeps doing that. So that's how this point is traveling along the hyperbola as the t increases. So we get, again, an interesting thing. If you're graphing this on some calculators, because of the way the calculators work, as this point goes up and to the right, the next point your calculator will determine is the one way down here to the left. And so they'll like connect those two dots as well. And so you'll see what looks like the asymptote. In any case, we see that this set of parametric equations gives us a graph, which is an interesting graph. It's a hyperbola. So these trig functions, x is equal to constant times trig function plus or minus another number, gave us some nice graphs. When we dealt with secants and tangents, we got a hyperbola. When we dealt with cosines and sines, we got an ellipse or a circle. And again, interesting conic sections there through these parametric equations. If we want to go in reverse, if we want to go from a conic section in rectangular coordinate systems to a pair of parametric equations, then I'm just going to go the exact reverse of what we just did. So I'm going to create something that looks like Well, if I'm trying to do cosines and sines, I'll try to create something that looks like something squared plus something squared is equal to 1. If I'm trying to deal with secants and tangents, I will try to use 1 plus tangent squared is equal to secant squared. So I 1 plus tangent squared equal to secant squared. So I try to get the version that I'm looking for on my Pythagorean identity. In this case, what I like to do is I like to say, well, we have something squared plus something squared equals a number. That's probably going to end up with cosine squared plus sine squared equals 1. And what I do is then I divide both sides by 49. That's going to give me x plus 3 quantity squared divided by 49 plus y minus 8 quantity squared over 49 is equal to 1. 49 is obviously a nice number because it's a perfect square. Therefore, I can rewrite that equation as a fraction like x plus 3 over 7 quantity squared plus another fraction being squared. That fraction being squared is y minus 8 over 7 equal to 1. Now I just recall that cosine squared of t plus sine squared of t is equal to 1. That's my Pythagorean identity. Traditionally, we associate the cosine with the piece that has x in it. And traditionally, we associate the sine with the piece that has y in it. And that's because of the relationship to the unit circle. And all we have to do then is say, because of this, I'm going to set x plus 3 over 7 equal to cosine. And I'm going to set y minus 8 over 7 equal to sine. That is sine of t. This is a pair of equations, one that relates x to t, and the other which relates y to t. And so we can solve each of those. When I solve each of those for, well, the first one for x, the second one for y, the first thing I would do is multiply both sides by 7. And then I would subtract 3 from both sides. That first equation becomes x equals 7 cosine of t minus 3. The second equation gives me y minus 8 is equal to 7 times the sine of t. If I add 8 to both sides, that solves it for y. And this is my set of parametric equations that will generate out this circle. I won't graph it. We know what the circle looks like. It's a circle of radius 7 centered at the point -3, 8. And notice that radius here is showing up as the coefficient of cosine and sine. The center is showing up as -3/8, shows up as the constants in that equation, in that pair of equations. Let's try another example. Here we have the equation, the standard version equation for the ellipse. Let's convert this rectangular equation into a pair of parametric equations. If you want to try this on your own, push pause on the video. I will show how it's done in a couple of seconds. All right, this one it's pretty obvious that we want to create something squared plus something squared equals 1, and then do our cosine sine substitution. Now, before I do my cosine sine substitution, I have to remember that the entirety of this object needs to be squared to replace it with cosine. So I need to rewrite this original equation into the quantity x over 6 all being squared, plus the quantity y minus 4 over 10 all being squared, and that can be equal to 1. Now that I've written it this way, I know that cosine squared plus sine squared equals 1. So I will set x over 6 to be my cosine. I will set y minus 4 over 10 to be my sine. By the way, traditionally, we put x over 6 as the positive cosine. And same thing, traditionally, the y minus 4 over 10, we set as the positive sign. But notice this would have also worked if you put a negative in front of your sign. And this would have also worked if we would have put a negative in front of the cosine. And this would have also worked if I would have swapped sine and cosine. Since cosine squared plus sine squared equals 1, it also is true that sine squared plus cosine squared equals 1. So if I use sine for my x over 6 and cosine for my y minus 4 over 10, it would have still given me the same graph, but that point on the graph would have been moving in different ways. So traditionally, we use the positive cosine and the positive sine when I do this indirect substitution. So the final set of parametric equations, when I solve for x, I get x equals 6 times cosine of t. That's just multiplying both sides by a 6. When I solve for y, I'd have to multiply both sides by 10 and then add 4. So that would give me y equals 10 times sine of t plus 4. That would be my set or my pair of parametric equations. At least one set of parametric equations that traces out the ellipse. Again, you could use other versions. You could use negative cosine, you could use negative sine, you could use negative cosine and negative sine. You could swap the sines and the cosines. It would just trace out the ellipse in a slightly different way. So there you go. that is your set of parametric equations that represents that ellipse. Let's do one more example with this hyperbola. So we have a rectangular equation, which we know is a hyperbola because we've seen conic sections before. And this hyperbola, we want to turn into a pair of parametric equations. Obviously, if you want to try this on your own, try it on your own, push pause in the video. I will do this in a couple of seconds. This problem has a couple of ways of approaching it. Now, they're all really, really similar. We have a Pythagorean identity, which says 1 plus the tangent squared of t is equal to the secant squared of t. One way to do this problem is to manipulate this equation, the rectangular one, so that I get 1 plus something squared is equal to something else squared. And that's perfectly fine to do. We just add this fraction to both sides, this y plus 1 squared over 81. We could have done that. I think I'm going to do it a little bit differently. I'm going to realize that if I subtract tangent squared from this equation on both sides, I end up with 1 is equal to secant squared of t minus tangent squared of t. Obviously, you can put 1 on either side. So I'll write it this way. If I write it this way, then I already have a form which matches my hyperbola form as far as which things are being subtracted and in which order. So I am going to use this version of the Pythagorean identity. Secant squared of t minus tangent squared of t is equal to 1. If you want to use this other version of the Pythagorean identity and add the fraction to both sides, that's perfectly fine too. In any, well, in the way I'm doing it, it would be x plus 7 divided by 12 quantity squared minus the fraction y plus 1 over 9 quantity squared set equal to 1. In our last example, like I said in our last example, I could have used either cosine or sine for the x part and either cosine or sine, the other one, for the y part. Here, I can't. Because of this minus, order matters here. So I need to have this first fraction be equal to secant and this second fraction be equal to tangent. This gives us two equations, one that says x plus 7 divided by 12 is equal to the secant of t, and the other which says y plus 1 over 9 is equal to the tangent of t. And just like previous problems, we can solve this by multiplying both sides by the denominator and then adding or subtracting this number. So when I solve for x, I'd multiply by 12 and then subtract 7. That would give me x is equal to 12 times the secant of t plus 7. No, I'm sorry, minus 7, excuse me, minus 7. I'd have to subtract 7 from both sides. And then y would be equal to 9 times the tangent of t minus 1. This would be a hyperbola centered at -7, -1. And you can tell by the way that this goes, it's going to be pointing right and left. Again, a couple of different ways to do that. I like using secant squared minus tangent squared is equal to 1. So manipulating my Pythagorean identity to make it look like the hyperbola form. But there you go. That's the set of parametric equations that gives this hyperbola. Now you could have, I didn't say this, you could have used the negative secant here instead of the positive secant. You could have used the negative tangent instead of the positive tangent, but traditionally people use the positive secant and the positive tangent when they set those up. So this is what we've done. With these indirect substitutions with the Pythagorean identity, we have seen that if we have equations in parametric where x is equal to a cosine t plus h and y is equal to b times sine t plus k, we get an ellipse whose center is at hk and whose horizontal axis length is 2 times a and whose vertical axis length is 2 times b. Now, I'm using A and B. I am not assuming A has to be bigger than B, okay, in this case. So sometimes the horizontal axis might be the major axis. Sometimes the vertical axis might be the major axis. It depends on whether or not this coefficient of cosine or the coefficient of sine is bigger. And with hyperbolas, we let x be equal to a tangent of t plus h and y be equal to b times secant of t plus k. Or we swap out the secant and tangent if the hyperbola is pointing the other way. So if the hyperbola is pointing left and right versus up and down, we have to use one set versus the other. And this is a hyperbola with center hk, and turns out has asymptotes, since I used the b with the y both times, has asymptotes with slope b over a and negative b over a. So the secant tangent parametrics gives us hyperbolas. Cosine sine parametric equations gave us ellipses. These aren't the only interesting parametric curves we can have. There's some weird ones, like if we have cosine to the third as our x value and sine to the third as our y value, we get this thing, which is called an asteroid. These graphs are all in the book that we use for my class. The hypertrochioid, I think that's how it's pronounced, is x is equal to 2 cosine of t plus 5 cosine of 2t, we get this weird star-shaped figure. We get an epicycloid, which looks kind of like a 3-leaf clover with some other ones. The rose curve is a well-known curve. And in parametrics, we can graph that by going cosine of t times sine of 4t is my x value, sine of t times sine of 4t is my y value. So you get lots of interesting parametric curves if we combine parametrics with trig functions. And these are obviously not the only ones. These are ones that are listed in our book, but not the only ones where we have interesting parametric curves. Now, let me just go back and state one thing. Remember, the advantage is that we have this new parameter, t. Oftentimes, we think of t parameter as being the parameter that's counting time. So what location are we at a certain point in time? So it tells us when we are at a specific point on the graph. So where the point is on the graph plus also when we are there. And this allows us to track movement of an object through the XY plane. If we are tracking movement, then one way to talk about tracking movement is the idea of orientation. As t changes, think of the movement of the point on a curve as it's moving through space. The orientation of the curve is the direction of movement as t increases. So the orientation of the parametric curve is the direction of movement as t increases. Let's look at a couple of different parametric equations. This pair and then this pair. I put brackets around this so we see it's a pair. Now, each of these are involving cosine and sine, so they're going to give us ellipses. And we'll see the orientation of each ellipse. You can do this on your calculator. I'm going to obviously do it on Desmos because of the way I'm presenting this information. Here we have x equals 3 cosine t, y equals 2 sine of t. And then we have x equals 5 sine of t, y equals 7 cosine of t. Let's graph each. If I'm doing this on Desmos, I would just graph it this way. I'd go 3 cosine t, comma 2 sine of t, and then I'd make sure that my t values are between like -10 and 10. Again, if you go from like 0 to just 1, then you only get part of the ellipse that I'm looking for. If you wanted to go a full rotation and just have one rotation, you let t range from 0 to 2 pi. Again, there will be a companion video on how to do this using the TI-84. It works a little bit differently. What I like to do when I track a point in Desmos is I copy and paste, and then instead of having a t, I just put in a slider. In this case, I put in a slider for variable A. And that will track the point. Now I used variable A. You can use any other variable you want as long as you can put a slider in. And then I grab this and I start increasing and I just see where the point goes. On the TI-84, you'd use your trace function to do this. So notice that as A is increasing, what's happening on this ellipse is we're moving counterclockwise. So counterclockwise is the orientation of this parametric curve. As as t increases, the point is moving counterclockwise. So that's the orientation. We have counterclockwise orientation on this ellipse. Now, let's do the other ellipse, the 5 sine of t, 7 cosine of t. Notice that initially, since I only let my t range from 0 to 1, I only get part of this ellipse. I'll make sure that my t ranges from at least 0 to 2 pi, but you could go further. And then what I like to do is I like to copy that and paste that and change the t to an a. Again, having this slider of a still exist. And then I use the slider of a to say, notice that as the a increases, the point is moving around the curve in a clockwise direction in this case. Therefore, the orientation, we would say, is clockwise orientation. We don't want to say left or right because there's times when we move left, there's times when we move right, there's times when the point moves up, there's times when the point moves down. But the proper terminology here is that we're moving clockwise. So this parametric curve has a clockwise orientation. Not all parametric equation pairs are going to give me an ellipse. Some of them will give me lines or parabolas. And so when we're talking about orientation of things like lines and parabolas, we may have to use different language than counterclockwise versus clockwise. Let's take a look at these two examples in example 15. The first is x is equal to 5 minus t squared. Y is equal to t squared minus 4. If you want to try these on your own, go ahead and do these on your own. In a couple of seconds, I will do these. Let's do the first one first. 5 minus t squared is the x. T squared minus 4 is the y. You may think and anticipate you're going to get a quadratic. It turns out it does not give you a quadratic. Let's see what it gives you. In this case, you get a line. Now, if you let t range from 0 to 2 pi, then your line is going to stop right here. So I'm going to let t range from like a positive 10 to a negative 10. Okay, maybe. Oh, I know why that's happening. Your line's starting right here because when we square things, we always get a positive number. sorry, so we start at 5, -4. Now this one's going to be tricky. Because we have that t squared, things go really quick. Notice what's happening to begin with. For negative values of t, or negative values of a, as we're increasing, we're moving towards the point 5, -4. Once I hit an a of 0 or a t of 0, then as we increase, we move back towards the left. So this orientation is kind of twofold. With negative a's, we are moving down and to the right as we increase. We hit the point 5, -4, and then for positive a's, we move up and to the left. Again, a little bit trickier to talk about, but that's what's happening. So if we're looking at orientation of this first parametric curve, we have to say for x less than 0, for negative numbers, we're moving down and to the right. Once we hit 0, then we're moving back up and to the left. And that's what's happening. Okay, so it's a linear movement down and to the right for negative x values and up and to the left for positive x values. Again, not as easy as a single word answer like clockwise or counterclockwise that we had in the previous two examples. Now let's take a look at this second pair of parametric equations. X is equal to -t, and y is equal to t squared plus 2. I have graphed this already and set my slider. So we're going to start increasing the value of t, or the value of, in this case, a. And when it hits the graph, we see this. As I start increasing, notice that this point is moving down, but left. And as I essentially hit the vertex of the parabola, then it changes back up and to the left. Now, all we are going to do in this case is say, well, the orientation is that the point is always moving towards the left. As t increases, or like I said, I use the slider A, as A increases, we are moving towards the left. And that's what I would write for my orientation. So don't worry about part of it's down, part of it's back up. That's just the nature of a parabola, but we're always moving towards the left. So we're moving left on this set of parametric equations, okay? And by the way, interestingly enough, if you just change this negative t to a positive t, you'd get the exact same parabola, but you'd be moving right. You'd have a right orientation. So changing this negative to a positive, changing that negative to a positive, we get the exact same parabola, but now as you increase your t value, you're moving right. Like I said, this is how to do this on Desmos. There are other ways to do it on different technology pieces. If you're using your TI-84 calculator, you use the trace button. But this is the idea of orientation. Movement of the point as t increases. So that is the end of this section. Obviously, we did a lot of graphing. We did a lot with conic sections, with parametric equations that turned into conic sections. There's a lot of other interesting parametric equations as well. And we'll take a look at some of those in the next section. Some of those we won't see in this class. But lots of interesting things that we can do with parametric equations.